Alright, gang, here we go. Chem 2, Unit 2. We're talking about atomic mass, periodic table, stuff about kind of like that stuff today. Real quick video. So, atomic mass unit, alright, AMU, because atoms have extremely small masses, we use a new system of measurement for their mass, where they call them AMU, called the atomic mass unit. Makes sense, right? But essentially, 1 AMU is equal to 1.66054 times 10 to the negative 24th grams. So it's a really tiny, obviously, right? Atoms are really tiny, so the AMUs are also really tiny. Okay, but essentially, in real world, when we're doing actual experiments, etc., we use large amounts of atoms. Even if we have a small sample, it's still a large amount of atoms and molecules. So instead of using the AMUs, okay, we'll use atomic weight. All right. Okay, and so then we have to calculate the atomic weight because there's so many of them. Remember, we have all these different isotopes. In the last video we talked about isotopes. So we have all these different guys that are in different isotopes, meaning they have different protons and neutrons. So we need to think about, well, what's its that, like, if we have a billion of these things, we don't really care if, like, what individual masses are for each element. We really just care about that average. So we're going to calculate the average atomic weight. And so in order to do that, we use this guy. So that's the sum symbol. Okay, so the sum of all the isotope masses times their fractional natural abundance for all isotopes. All right. So essentially, we just take the mass of the isotope, and that's easy to find with a mass spec. We'll talk about that in a minute. And the fractional natural abundance. All right, so this is going to be usually, so like fractional natural abundance is just a fancy way. So we take the natural abundance, or the abundancy of it, all right, and then if it's a percentage, we need to turn it into a fraction. All right, is essentially what that means. So we take each individual mass times its abundance and then add them all together. All right. So here's how we find atomic weights. All right. So this is called a mass spectrometer. Okay. So we've got a tube. Usually this is in either a vacuum, or sometimes it's a neutral gas, like a noble gas or something like that. And so you inject your sample right here, and then it gets ionized. Okay, so it gets ionized, and it's gonna become cations. All right, and it shoots through here, and it speeds it up really fast, and then it sends it around this corner using a magnet. Now, if you think about it, if you're driving a semi truck and you try to take a corner too fast, say like you're taking a semi truck, a pickup truck, and a motorcycle, and you're trying to go around a corner, and each of you are trying to make the fastest corner you can, going 20 miles per hour. Well, who's going to make the fastest corner? Obviously, the motorcycle will be able to go around the corner faster than the pickup or the semi, right? So the motorcycle will be able to go around the corner the fastest, and so it's going to make the corner the tightest. Same thing happens here, but at the atomic level. These guys here, they'll come through here, they'll get faster and faster, accelerate through, and then they'll come and make the corner. Since the ones that are less light, they've all been ionized equally. All of them are Cl plus, but the isotopes that are lighter, meaning the isotopes that have the smaller number of neutrons, they'll be able to go around the corner just slightly tighter, and then the more heavy ones will go around slightly less tight. All right, so then we can stick on the end, we'll take another one of these discs with a slit in it, and then we can move this slit back and forth so it isolates just that particular isotope. Okay, so by moving this guy back and forth, we can capture just the Cl35s or just the Cl37s. All right, and then we can detect them on the other side. And when it spits out, we get a graph kind of like this guy over here. So this is the atomic mass over here, so we know that there's an isotope at 35 and there's an isotope at 37. All right, and then based on their signal intensity, okay, so this is just kind of essentially like how strong was the signal, we can also use these to get a relative ratio of how much, okay? So it looks like Cl37 is about 30% as likely as Cl35, more or less, kind of just depending what this based on this graph over here. All right, so that's kind of how a mass spectrometer works. So it sends these ionized gases around a corner super fast, and because they're going super fast, trying to make a turn, the lighter elements are going to get separated out from the heavier elements because they're able to go faster. All right, so they come around and then they can get separated out. All right. Okay, so let's do a little practice here where we're calculating atomic weight. So we've got 3 isotopes of silicon in nature. 28 silicon, it's 92.23, and its atomic mass is that, etc., etc. So in order to calculate the atomic weight, remember we take the sum of the isotope mass, I'll just say isotope mass, all right, times, I put a bracket, times the percent abundance. But we got to turn it into a fraction. All right. So we'll take this guy. So first one is silicon, 28. So its atomic mass is 27.97693, and its percent abundance is 92.23. So it'd be 0.9223. All right. So that equals, all right. And so you have to do this kind of in individual steps. Otherwise, sig figs will kind of screw you up. So 27.97693 times 0.9223. All right, I got 25.803. How many sig figs? Well, the percentage is 4, so my answer should have 4. So 25.80. All right, so that's one, 25.80. All right, now we got to do the next one here. The next one is silicon 29, and this is its percent and its mass, so we'll take 28.97649 times its percent abundancy, which was the 0.0468. Remember, we have to turn it into a fraction or a decimal. Okay, we're going to multiply that out, so 28.97649 times 0.0468. All right. Now this guy only has 3 sig figs, so it'll become 1.36. All right. And I recommend making sure that the decimals are lined up here. All right. And the last one is we have 29.97377 times its percent abundancy, which is the 0.0309. Okay. 29.97377 times 0.0309. We get 0.926, 3 sig figs, so it becomes 0.926. All right, 926. All right, now we're going to take all those guys and we're going to add them up. Now remember, when we add these up, adding sig figs, this guy stops at the hundredths, so our answer needs to stop at the hundredths. All right, so we'll say 25.80 plus 1.36 plus 0.926. All right, and we get 28.086, but round to the hundredths, it becomes 28.09. All right, 0.09. Now notice that this number, which atomic mass are we closest to? Well, 28.09 is closest to the atomic mass of silicon 28. And that makes sense because it was also the most abundant. Okay, makes sense that the most abundant one is the one that's going to affect our average atomic mass the most. All right, so that's how you do those guys. All right, here's the periodic table. Should be pretty familiar with it. All right. So we've got the elements are all arranged in order of atomic number. Okay, atomic number is essentially the number of protons. All right, so hydrogen has 1 proton, helium over here has 2, lithium 3, 4, 5, 6, 7, 8, 9, 10, etc. Cool? And then we can arrange them, or let's talk about these boxes real quick. So the middle symbol, okay, tells us the atomic symbol, all right? The top number is the atomic number. Again, this is the number of protons, all right? And then the atomic weight, and that's the average, right? So this is the average, and this is what we just calculated in the previous work, all right? Groups, all right, are the columns, okay? So the groups and the rows are called periods. So remember in class we say, and you're in a group, period. And you're in a group, period. You're in a group, right? I put you in a group, and that's it. You can't change your group. You're in a group, and that's period. Okay? So things that are in the same group have similar properties. All right? So we'll talk about some of those. Okay? Now, the reason the periodic table looks the way it does is because of the patterns that evolve. All right? So we've got hydrogen, and then it gets a non-reactive gas, and then a soft reactive metal, and then beryllium, and then we get fluorine, which is very similar to hydrogen, and then we get a non-reactive gas, and then a soft reactive metal. See this pattern? We get these repeating pattern. This is called periodicity. So as you move across the row or the periods, you start to see a pattern evolve. All right, and so that's why the groups, the periodic table has this funny shape, right? Notice how it's got this like very distinct, like this row has 7, but this row only has or this column has 7 or group, and this column only has 6, and these only have 4, right? And we kind of get this weird shape to it, and that's because we're arranging it to make it easier to predict properties. All right. There's a really fascinating book about the organization of the periodic table and Mendeleev and all that stuff called The Disappearing Spoon. Very worth reading if you're interested in that kind of thing. All right, here's the groups that you should be familiar with. All right, the alkali metals are in group 1A, so that's that very first column. These guys, when you stick them in water, they react, they blow up. Francium, super unbelievably reactive. It's got such a short half-life that it's really hard to like actually see how much it reacts. So it's actually like most of the time, if you see a video, most of the time it's just a simulation of what would actually happen. The alkaline earth metals is the very next column over. These guys don't really react with water very well, but they'll react readily with an acid. All right, so if you stick a chunk of magnesium in some hydrochloric acid or something, you'll get a fair amount of bubbles and hydrogen formation and stuff. The chalcogens are 6A, so these are the guys right before the halogens, or like if you start at the back or the last row is the noble gases, and then you get the halogens and then the chalcogens. All right, and these are the chalcogens. All right. And these guys are the oxygen, sulfur, selenium. Okay, they all have very similar properties. This one's probably the least common word of everything, like out in the real world. Most people don't ever use this term. And then these guys are the halogens. All right, 7A. So these are fluorine, chlorine, bromine, iodine. We mess with these guys all the time because they're very, very reactive. And then finally, the last column or the last group are the noble gases. And these guys are called noble because they just don't participate in any of the little, the minor elemental skirmishes the other elements participate in. All right. So if you imagine like a stair-step line going across like this, all the way down the periodic table, kind of divides the periodic table in two parts, the left and the right. The metals are all the ones on the left, all right? So these guys are all metals. So in this, they're kind of like the ones that are kind of like this pale yellow color. All right, the only one that's a little bit different is hydrogen. Hydrogen is a non-metal, but we stuck him over here because he kind of acts more like lithium, sodium, and all these guys. All right. Metals are all relatively shiny. Okay, they've got luster. They conduct heat and electricity, and they're all solids except for mercury. Mercury is a liquid at room temperature. All right. Non-metals are on the right side. So in this specific one, they're kind of like this pale green color. All right, and they're on the right side, and then hydrogen is included with those non-metals. All right. For the most part, a lot of them are gases, some of them are solid, and then one of them is a liquid, and that's bromine. Bromine is a liquid. But like phosphorus, sulfur, and carbon down here in this picture, these are all solids at room temperature. But like fluorine, oxygen, nitrogen, those are all gases at room temperature, as well as the noble gases. All right. These guys that appear right next to them, now you have to be kind of careful, like palladium is not a metalloid, neither is aluminum, but the boron, silicon, germanium, arsenic, antimony, and tellurium, these guys are all metalloids. So that sometimes they're kind of like metals, like silicon is actually pretty shiny, like it almost looks like aluminum, but germanium kind of looks more like carbon. And it doesn't have much luster. Okay, so they're also known as semiconductors. So they're very important in making microchips and the like. All right. And that's all we're going to go for this video here. Told you it was a short one. Let me know if you have any questions.